Okay, so elliptic equations are actually another specialization of the advection diffusion equation. That is, okay, so in the advection diffusion equation, I actually forget to add a term. The term I forget to add is another term that is a function of x and t on the right-hand side. I mean, it's a term that we don't necessarily want to investigate that much because it's actually a non-differential term, right? So adding that term doesn't seem to be very in the realm of study of differential equations. But if you get rid of if you get rid of too many terms, this is the only term that is going to be remaining important, which is actually in the elliptic equations. So in elliptic equations, you are describing a solution where u is equal to 0 and the time derivative is also equal to 0. So if you put both terms 0, the only remaining, there is no term on the left-hand side anymore, right? And the only remaining term is on the right-hand side. So you have kappa times second-order derivative and plus f. I mean, the reason we are keeping f here is if you get rid of f, you get the second-order derivative equal to 0, which means you have a straight line, right? So having f here actually makes the elliptic equation more interesting. So this also describes what happens in real life, but in equilibrium. In equilibrium means everything has settled down. For example, if you look at a heat transfer problem, you would be asking the question, what's the distribution of temperature on the bar, for example, when you are heating the bar and when the temperature of the bar no longer changes anymore? Okay, so this is one of the questions described by this equation. Similar equation would be used in describing the behavior of structure. So one thing people use in practice for solving elliptic equations is designing structures, for example, buildings. And in designing buildings, you want to make sure the building is actually wouldn't collapse when you put some weight on top of it. And one of the cases is so-called dead weight, right? So which means it's a static loading, and the response of the structure would be also static. So that type of analysis would require solving an elliptic equation, which means solving the loading, stress, and strain of the structure when the time derivative is equal to 0. So that also describes a real-life engineering scenario. But as you can see, there is no time involved. All the independent variables of that x is of that unknown solution is space. If you're solving a three-dimensional structures, there are three axes, x1, x2, x3, and here x would be a vector, right? But still, it's an elliptic equation. You cannot separate a single variable, either x or y or z, that has that characteristic. If you put a loading somewhere, it only affects the stress and strain of the structure on certain side. There is no t you can pull out of the independent variables.